Welcome to solverfy.
In this problem, we have a soap film suspended in air with white light incident upon it. So we can draw this as, here's our soap film, which has some thickness L. And we're told it has an index of refraction of 1.33. And on either side, we have air. And air has an index of refraction of 1. And so what's going to happen here is light is going to shine incident on this first surface, and part of it's going to reflect. But another part of the light, some other fraction of the light, is going to transmit and reflect off the back surface. And so in total, we're going to have two rays that are being reflected. And these rays in general will be phase shifted one from the other. If this phase is exactly some multiple of the wavelength, then you have a maximum reflection. And if it's a multiple of half the wavelength, then you have minimum reflection. We're told that for two different wavelengths, which I'll call lambda 1 and lambda 2, which are given as 600 nanometers and 450 nanometers, that lambda 1 we have a max, and lambda 2 we have a min, and that there are no max or min between them. So these ones are in sequence, right? You can imagine you've got a maximum and a minimum, and so these are one right after the other. So let's just look at lambda 1 first. So if there's a max, that means that the incident light comes in, and the extra distance traveled by this red ray here, which is twice the thickness of the material, is going to be exactly some multiple of the wavelength. So we can write that as the extra distance traveled, which is 2L, has to equal the wavelength, lambda 1, but it's actually not lambda 1 because this is the vacuum wavelength. It's lambda 1 in this material, which is lambda 1 divided by the index of refraction, and it's some multiple of this. So we can write this as times m, where m is an integer. And I've put some parentheses, open brackets here, because we might have to add something here. So let's check. So because what happens is, if you go from lower index of refraction to higher index of refraction, the reflected ray is actually reflected half a wavelength out of phase, or phase shifted. So we might have to correct for that, because so far we've assumed there's no phase shift on these reflections. So let's see. We're going from N1, or N of air, which is 1, to N of the soap film, which is 1.33. So on this first surface here, there is a phase shift. So that means that this whole equation, as it's written, is half a wavelength off. When we go and look at the back surface, we're going from a higher index of refraction to a lower index of refraction, so the red ray doesn't get phase shifted. So we're going to have to either add or subtract half a wavelength to this equation to correct for this phase shift of the black ray. So I'm going to subtract 1/2 here. For lambda 2, we're told that it's a minimum, and it's just off from lambda 1 by half a wavelength, which means that the original equation we wrote was actually correct for lambda 2. So we can write 2L lambda 2 over n times m, and this will give us a minimum. And so now we have these two equations, and they're both equal to twice the thickness. So we can solve, or we can equate these two. So we have lambda 1 over n times m minus 1/2 equals lambda 2 over n times m. Right? So the n's cancel, and we can isolate m. So we're going to have m times, here we have a lambda 1, and we got to bring lambda 2 from the other side. And that's going to equal this lambda 1 over 2, which I'm bringing to the right side. So it's negative, now it's positive. So lambda 1 over 2. And so we find that m must equal lambda 1 over 2 times lambda 1 minus lambda 2. And this has to be an integer. It better be, because m has to be an integer. So if we plug in what lambda 1 and lambda 2 are, which was 600 nanometers and 450 nanometers, we find actually that m equals 2. So that's good, because it has to be an integer. So that means we didn't do something wrong. So now we can go back and plug m into one of these two equations. I'm going to plug it into the bottom one. It'll be simpler. So I'll do it over on the side here. So we have that 2L equals lambda 2 over n, and then times m, which is 2. And so we find that L equals lambda 2 over n, and this turns out to be 338 nanometers.